Yes, the title of the talk is a sequence of means converging to a mean. It is well known that if a sequence of rational numbers converges, then it converges either to a rational number or an irrational number. It is interesting to note the examples of sequences of rationals converging to irrational numbers. One such familiar example is the sequence whose nth term is an is equal to 1 plus 1 by n whole raised to the power n, where n is a positive integer. That is n is equal to 1, 2, 3, 4, so on. Now note that 1 over n is rational number, then 1 plus 1 over n is also rational number, and when we raise its power n, where n is equal to 1, 2, 3, 4, so on, then again this is the rational number. So the terms of this sequence are rational numbers, and this sequence converges to an irrational number. This irrational number is denoted by E exponential and is a mathematical constant known as Euler's constant. It is same as base of the natural logarithm. It is approximately equal to 2.7182. One can find several other examples in literature of this type when sequence of rational numbers converges to irrational numbers. In literature, in this context, we find an interesting sequence of means converging to a mean, and we discuss this here. The particular cases of this sequence give sequence of rational numbers converging to irrational numbers. For this, we consider the arithmetic mean, geometric mean, and harmonic mean of two positive real numbers, a and b. Arithmetic mean is defined by a plus b by 2, a of ab is equal to a plus b by 2, and geometric mean is root ab, and harmonic mean 2 over 1 over a plus 1 over b, and this can be written as 2ab over a plus b. Now we have well-known arithmetic mean, geometric mean, harmonic mean inequalities. That is, harmonic mean is less than equal to geometric mean, less than equal to arithmetic mean. So this expression 2ab over a plus b, this is less than equal to root ab, less than equal to a plus b by 2. And equality holds in this first inequality if and only if a is equal to b. And equality hold in the second inequality if and only if a is equal to b. Otherwise, both the inequalities remain strict inequalities. Now take these two positive numbers, a and b, and let b1 is equal to a plus b by 2. That is, b1 is arithmetic mean of a and b, and a1 is equal to 2ab over a plus b, and this is harmonic mean of a and b. Now b1 lies somewhere here in the middle of this line, and harmonic mean is less than equal to arithmetic mean, therefore a1 is someone here. Now take a1 as one positive number and b1 as other positive number, and repeat the above process. That is, let b2 is equal to a1 plus b1 by 2. Then b2 is somewhere here, and a2 is harmonic mean of a1 and b1, and a2 is somewhere here. Now if we repeat the above processes, we find that we get this sequence, and this is an increasing sequence, a1, a2, so on. And similarly, we have this decreasing sequence, b, b1, b2, so on. So from here, we expect that this sequence of AIs converges somewhere here, and this sequence BIs also converges somewhere here, because From here, we see that all the terms of both the sequences are bounded because both lies between A and B. Now we prove this mathematically. We have this sequence. First term is A, B. Then A1 is 2AB over A plus B. A2, 2A1, B1 over A1 plus B1, where B1 is A plus B by 2. In this way, we have this sequence. And also we have this second sequence of B i's. Now this sequence, as discussed above, AN is increasing sequence and sequence BN is a decreasing sequence. Now we know a monotonically increasing sequence which is bounded above is convergent sequence. We mean by convergent that this limit n goes to infinity xn exists and is a finite real number. And this limit is equal to least upper bound of this set xn such that n belongs to capital N, where capital N is set of natural numbers. Likewise, every monotonically decreasing sequence which is bounded below is a convergent sequence. Now, both the sequences AN and BN are bounded. Why? Because each AN lies between A and B. And likewise, each BN also lies between A and B for all n. So AN and BN are convergent sequences. Also, we have AN is less than equal to BN for all n belongs to capital N. Why? Because AN is harmonic mean of two positive real numbers and Bn is arithmetic mean of same two positive real numbers. So from this we have 0 is less than equal to Bn plus 1 minus An plus 1. Why? Because Bn plus 1 is greater than equal to An plus 1. Now substitute value of Bn plus 1 and An plus 1. We have this equal An plus Bn by 2 minus 2 An Bn over An plus Bn. Simplifying this, we have this expression. Now, in this first term, Bn minus An is non-negative and An plus Bn is greater than equal to Bn minus An. So this term, Bn minus An over An plus Bn is less than equal to 1. So ultimately, we have this inequality. Bn plus 1 minus An plus 1 less than equal to Bn minus An over 2. Now we can take limit both sides, limit n goes to infinity, then Bn plus 1 minus An plus 1 is less than equal to limit n goes to infinity, Bn minus An by 2. Now since An and Bn are convergent sequences, therefore limit n goes to infinity n plus 1 is same as limit n goes to infinity An. And say this equal L1. And similarly, limit n goes to infinity Bn plus 1 is equal to limit n goes to infinity Bn is equal to L2. Now use the fact that if xn is less than equal to yn for all n, then limit n goes to infinity xn is less than equal to limit n goes to infinity yn. So what we have from this relation Bn plus 1 minus An plus 1 less than equal to Bn minus An by 2. We have L1 minus L2 less than equal to L1 minus L2 by 2. And this is possible only when L1 minus L2 is 0. So we have L1 is equal to L2. That is An and Bn converges to same limit. Alternatively, we can show this by using squeeze principle. We have 0 is less than equal to Bn minus An. And from here, inductively, we have Bn minus An is less than equal to B minus A over 2 raised to the power n. And limit of this when n goes to infinity, limit n goes to infinity, B minus A over 2 raised to the power n, this goes to 0. So by squeeze principle, we conclude that limit n goes to infinity, Bn minus An goes to 0. That is Bn and An converges to same limit. Now write An plus 1, Bn plus 1. Substitute value of An plus 1 is equal to 2 an bn over an plus bn, and bn plus 1 is equal to an plus bn by 2. And this comes out to be equal to an bn. So we have an plus 1, bn plus 1 is equal to an bn is equal to so on up to is equal to ab. So when we take limit n approaches infinity a and bn, we can write this equal limit n goes to infinity ab. Why? Because a and bn is equal to ab. Now an and bn are both convergent sequences. Therefore, this left-hand side expression is equal to limit n goes to infinity a and limit n goes to infinity bn. But limit n goes to infinity bn is equal to limit n goes to infinity an. So left-hand side is limit n goes to infinity an whole square. And this equal ab. So limit n goes to infinity an is equal to root ab. So this sequences of means converge to geometric mean of a and b. And similarly, we have this second sequence, limit n goes to infinity bn is equal to root a b. So this is one example. If we take a is equal to 1, b is equal to 2, this is the sequence formed a i's. By taking first term arithmetic mean of this, then taking arithmetic mean of a1 and b1, we get a2 and so on. And this is the second sequence. These AIs are obtained by taking harmonic mean of A note and B note. And the second sequence is obtained by taking arithmetic mean. Also note that A4 is strictly less than B4. Up to some decimal of places, they are same. But otherwise, A4 is strictly less than B4. As discussed above, both the sequences converges to root AB, that is root 2. Now, similarly, if we take b is equal to 3 here, we can find sequences which converges to root 3. And if we take 7 here, then we can find sequences converging to root 7. Actually, this was an algorithm used in computer programming to evaluate the under root of natural numbers. Thank you.